In this example, we're looking at a motorist that's driving a 1,000 kilogram car, and she wishes to increase her speed from 20 meters per second to 30 meters per second in 5 seconds time. So with all of that given information provided, we need to know how much power, in this case horsepower, is required to accomplish this. Now, the standard unit of measure for power is the watt, so be mindful of that. We do need to make a unit conversion at the end here. 1 horsepower is approximately equal to 746 watts. Now, we need to know power, and power is really just the change in work. Well, I guess more appropriately, we should say that it's the change in energy over time, where work is defined as the change in energy. So if we follow this progression of explanations, work being the change in energy, and the change in energy in this case, since it's all motion, is kinetic energy final minus kinetic energy initial, we can simply substitute all of our components into this form of kinetic energies. So half times mass times velocity squared in both components. The half mass is a common factor, so I've factored that out, and I've used velocity of 30 and 20 for our final and initial velocities. When we simplify or execute this, I should say, in our calculator, we end up with 50,000 watts. And since we need to find horsepower, we'll take the number of watts, divide by 746 watts per horsepower, and that comes out to be approximately 67. In number 12, we again have a question about power. It takes 27 seconds for a crane to lift a 55 kilogram object, a vertical distance of 18 meters, at a constant velocity. And that's helpful for us when we compute this result. So what rate is work being done here? Now, my calculus students might see that word rate and automatically think derivative, but I don't want you to take a derivative. That's not really what we're doing here. We're just kind of emphasizing that work in and of itself is a component of a rate when we talk about power. We have work divided by time. That's our rate measurement, if you will. And work divided by time is the definition of power. So if we have the time value supplied, if we have the mass and the distance that an object travels, the last component that we need to consider is the gravitational constant, where the force in this case is played by gravity, mass times the gravitational constant, times the distance that the object travels divided by time, and we end up with 360 watts of work being done. Or I shouldn't say watts of work as a total measurement, but the energy necessary to move this object at this rate of speed is 360 watts of power. So I think that was the last question from Chapter 7 in this practice test. We move on to Chapter 8, where we talk about momentum and collisions. If we have two objects of different masses that collide, the impulse they exert on each other are blank. Well, remember, impulse, I'm going to go ahead and label that as J, even though our textbook was calling it I for some time. The impulse is equal to the force, the net forces of the collision times the change in time. I just realized I've got this arrow pointing in the wrong spot. Because the net force is the same for all objects that are in the collision. Think Newton's third law, where every action has an equal and opposite reaction. If the net forces are the same for the objects, then and the time of the collision remains the same, then the impulse has to be equal but opposite as well. So the time for both objects is exactly the same, but the forces that are experienced are equal and opposite. So therefore, the calculated impulse, J, is also going to be equal and opposite. And that's true for all collisions. With number 14, we've got a 2 kilogram object that's moving along an x-axis, so basically forward and backwards. The velocity in the x direction is negative 2 meters per second at time 0, and we would like to know what the velocity is at time equals 2. So you can see that according to this graph, at the beginning of this event, we had a force of 4 newtons, and as the event progressed, we had a constant force for a little bit, but then our force was decreasing and then ultimately became negative. So the force ended up being directed in the opposite direction. So what's going to happen here? Well, the impulse, J, is equal to force times time. When the vertical unit on our graph is force and our horizontal unit is time, then we can obtain this calculation by finding the area under the curve. Now, we don't actually have a curve here. That's another trapezoid. So if we recognize the area of this trapezoid to be 6 units, and we combine that with the other components of our formula here, which, by the way, I'm using a slightly different form of the formula. I'm talking about the change in momentums, where mv is momentum. So we have final momentum and initial momentum. I'm using that so that we can isolate our final velocity. We can get at this component because we know the joules, we know the, not joules, we know the impulse, we know the mass, and we know the initial velocity. So we should be able to calculate the final velocity with that component, and it appears to be 1 meter per second. Since it's positive, we'll go ahead and mark that as positive. And we know that even though the force direction has changed from a positive force to, well, what's becoming now a negative force at the second, at t equals 2, the object is still moving forward at 1 meter per second. For number 15, this is kind of an interesting problem because it's another way to note an inelastic collision. We've got two objects with two different masses and two different velocities that end up combining into a single object with a single velocity. This new object has the combined mass of the first and the second, but the velocity, since the two objects are essentially stuck together, the final velocity is a single component at the end. So if we know that the mass of the boy and the, we don't know the mass of the cart, but we know the mass of the boy and the velocity of the boy and the cart at the beginning and end, because the cart was at rest at the beginning. We know all of these components here after picking through the problem. We can substitute that into the inelastic collision formula, and again we know the initial velocity and initial mass. Since the initial velocity of the cart was 0, so this was the boy and this one's the cart, so the boy and the cart had a velocity of 0, so it had no momentum at the beginning, but as we isolate the components necessary to find the mass of the second object, we can do so and determine that it ends up being 150 kilograms. So I think that's a good stopping point for this video. We'll finish up the remaining questions of the test in the next one.